the condensate is basically a laser beam, but it's okay. A laser is a non-equal. Okay, what a laser is a Froelich. What a laser is a Froelich condensate of photons, and but the photons can propagate in vacuum. Okay, what the Froelich condensate is a laser beam of these emergent collective excitations inside the material that are confined inside the material. So basically, what a Froelich condensate is essentially is like a room temperature superconductor. See, superconductors,
Mm-hmm.
electrical superconductors,
Mm-hmm.
and also neutral superfluids, they only exist at low temperatures in thermodynamic equilibrium. But with the Froelich effect, you can get basically room temperature superconductors and room temperature superfluids by pumping it, because basically it's a laser. That's what a laser is. A non-equilibrium. What happens? You pump the system. You have to do it at the right frequencies. It's like a resonant effect. So if you're at the resonance, so to speak, roughly speaking, above a certain critical power threshold, you get the coherent effect.
And then what you do
It's like
is,
negative temp. Yeah, go ahead.
oh, so you also
Go
talk
ahead.
about
You want to
slow
say something?
light.
Go
So
ahead.
it goes down to 3 centimeters per second within the material, right?
Yeah, that's very rough because again, I'm really talking about near field. It's just like that's an imperfect analogy because uh, okay, the coupling, the Einstein coupling is a fraction. It's electrogravitic. You know,
Mhm.
it's Newton's G. It's the big G in the numerator. In the denominator is the fourth power of the speed of light. It's supposed to be the vacuum speed of light. Okay, but you really have to use the material speed of light, and because of index of refraction, generally the speed of light in ordinary materials is much smaller because of refraction. The index of refraction is bigger than one. Now you can make these special materials where the index of refraction gets less than one, in which case you go the other way. You can actually make the effective speed of light inside material even faster than the vacuum speed. But we're interested, but because G over C to the 4 is the coupling of the, say, stress energy, say electromagnetic stress energy creating gravity, transforming electromagnetism to gravity is proportional to big G over C to the 4. So if you make the effective C small, that means you get a big gravity field with a small amount of input, energy density. So that was that idea.
I see.
And
And
that
then
was,
you're
but
also
until,
increasing the
that was,
negative and permittive. Sorry, go ahead.
no, go ahead, what?
Also, you're saying
Go
you're
ahead, what?
enhancing the
What are you going to say?
negative permittivity, and then also, how Puthoff's equation C
Okay,
equals.
wait, no, you want, actually, see, that's why it's hard to do this with just words, with
I understand.
visuals in the blackboard. The fraction is G over C to the 4. You want to get that fraction big. So what you want to, you keep the numerator fixed. It's a fixed G, the fixed Newton's gravity constant. But in the material, you can make the speed of light smaller, so to speak, and therefore the fraction gets bigger, and that's what you want. So you want the speed of light. So you don't want negative there. You want ordinary positive. Now there'd be other applications where you want it to go, to negative refraction. But that's a separate thing. Those are different applications. For propulsion, for the UFO propulsion problem, you want the index of refraction to be positive and big. But then
I
there's
see.
also something else. It also has to be, index of refraction is actually a complex function. There's the imaginary part. It goes, there's the real part of the index, and there's the imaginary part because of dissipation. Basically, the real part of the index of refraction, from a quantum field theory point of view, is photons doing what are called forward elastic scattering off, say, electrons. Okay, and that's the real part of the index of refraction. The imaginary part is inelastic scattering, heating, where you lose energy, where the photon frequency goes down because it's dissipating, it's what's called inelastic collision. And that makes an imaginary part. Now, as it turns out, the ratio of the imaginary part of the index of refraction to the real part, that ratio can switch the sign from attractive gravity to repulsive anti-gravity. See, none of these people know any of this, but this is that's the other thing. So there's all for that. But all of that is classical. It's only for what's called bosons. See, photons are bosons. Bosons scattering spin one. Photons are spin one particles, and they're scattering off spin one half electrons. But you also have this new effect, the quantum spin effect, and that's where the torsion comes in. And the coupling of the torsion waves to what's called the tor. Well, okay, what you have in matter, technically, you have in materials, you have what's called a spin density tensor. That's not true for all materials. It's only special materials. Not every material has a spin density tensor. You have to, you have to construct them in a certain way. They have to be like ferromagnets or ferroelectrics, or you have to make artificial metamaterials. You have to actually use nanotechnology bottom up and just create from the bottom up the kind of material you want, which is what these aliens have. They have very sophisticated condensed matter, nanotech physics, or maybe even sub-nanotech, down to angstrom and maybe even lower than that. But in any case, so you have to have these special materials in which you have these spin density tensors. It's like how many spins are all spinning the same way per unit volume. Okay, it's called spin density, but it's actually a tensor, and so you have to have that. Not every material does that, but the way the spins connect to the torsion is very strong. It's extremely strong, much strong. Okay, and then you have what's called a quadratic effect. You have it's the square. Basically, it's the square of the spin density that creates the ordinary gravity. Okay, and then and so what you actually have the square of the square of this coupling that's already strong, and it comes to the second power, quadratic power. So it's really like super strong. So the point is, this stuff can be can actually be dangerous. You've got to be very careful here. Proceed with caution because you're dealing with this is an unknown quantum spin property of matter that people are not very aware. I'm sorry when I say people, I mean other physicists. People like Kevin Knuth, the guys, who are the guys doing, even Hal Puthoff, who are the guys.